Imagine you are standing outside on a clear night and you look up at a star. You are not seeing that star as it is, you are seeing it as it was, years ago, perhaps thousands of years ago, because the light traveling from that star to your eyes took time to arrive. The star you are looking at may no longer exist. It may have collapsed, exploded, or gone dark centuries before your grandparents were born. And yet its light is only reaching you now. This is not poetry, this is physics. The speed of light, approximately 299,792 kilometers per second, is not merely a number, it is a law woven into the architecture of the cosmos. It determines how information travels. It determines how cause and effect are connected across space. It determines the shape of time itself. But here is the question that will guide us today. What if that number were different? What if, instead of nearly 300,000 kilometers per second, light traveled at, say, the speed of sound, or the speed of a bicycle? What kind of universe would we live in? What would we see? What would we be? Hold that question, because the answer reaches far deeper than you might expect. Before we change the speed of light, we need to understand what it actually does, what role it plays in the universe as we know it. Most people, when they hear speed of light, think of a fast thing, a record, the universal speed limit. That framing is correct, but incomplete. The speed of light is not simply the speed at which photons travel. It is the speed at which causality propagates. It is the rate at which any change, any signal, any piece of information can move through space. It is the conversion factor between space and time, the number that decides how those two seemingly different things are actually unified into one fabric called spacetime. When Einstein developed his special theory of relativity in 1905, he began not with the idea of fast-moving particles, but with a much deeper question. What would the universe look like if the laws of physics, including the behavior of light, were the same for every observer, regardless of how fast they were moving? The answer forced him to conclude something radical. Time is not absolute. Space is not absolute. They are relative. They depend on how fast you are moving. And the quantity that holds everything together, the fixed point around which space and time flex and warp, is the speed of light. In Einstein's equations, the speed of light appears not as a speed in the conventional sense, but as a structural constant, a ratio that defines the geometry of the universe. Change it, and you do not merely make light slower, you change the relationship between space and time. You change how gravity works. You change how energy and mass are related. You change everything. This is why the question matters. We are not asking about a minor adjustment to traffic flow in the cosmos. We are asking what happens when you reach into the deepest machinery of reality and turn one of its fundamental dials. Let us begin carefully. Let us build our intuition in layers. Light, in a vacuum, always travels at the same speed. This is one of the most tested, most confirmed facts in all of science. It does not matter whether the source of the light is moving toward you or away from you. It does not matter whether you are moving toward the light or away from it. The speed of light, measured by any observer in any state of motion, is always the same. This is strange, profoundly strange. If a train is moving toward you at 100 kilometers per hour and throws a ball forward at 50 kilometers per hour, you observe that ball moving at 150 kilometers per hour. The speeds add. But light does not behave this way. If that same train shines a headlamp, the light from that headlamp does not travel at the speed of light plus the speed of the train. It travels at precisely the speed of light, no more, no less. The universe conspires, through changes in time and space themselves, to keep that number constant. The reason, as Einstein revealed, is that space and time are not separate fixed containers. They are flexible. They stretch and compress depending on your motion, and they do so in precisely the way needed to preserve the constancy of the speed of light. Now, let us reduce it. Suppose, through some thought experiment, we reduce the speed of light to 1 meter per second, the speed of a slow walk. Step outside. Look at the sun. The sun is approximately 150 million kilometers away. At the real speed of light, sunlight takes about 8 minutes to arrive at Earth. At 1 meter per second, it would take approximately 4.7 billion years. That is nearly the current age of the Earth itself. The sunlight you would see would have left the sun before the Earth was formed. But this is just geography. The consequences go much deeper. Einstein's most famous equation, and perhaps the most famous equation in the history of human thought, states that energy equals mass multiplied by the speed of light squared. This equation tells us something extraordinary. Matter is frozen energy. The protons in your body, the atoms in the chair you sit in, the iron at the core of the Earth, they all contain enormous amounts of energy locked inside them. The reason they contain so much energy is precisely because the speed of light is so large. When you square a very large number, you get an almost incomprehensibly large number. That is why a small amount of mass can release a catastrophic amount of energy. Now, suppose the speed of light were 1 meter per second. Squared, that's 1 unit. The energy contained in a kilogram of matter would drop by a factor of roughly 10 to the power of 17, 100,000 trillion times less than in our universe. Nuclear reactions, the processes that power the sun and every other star, would release almost no energy. Stars could not shine. Not because the fusion process would stop, but because the energy released would be so negligible that it could not sustain the enormous temperatures needed to keep the reaction going. In a universe with a very slow speed of light, there would be no stars. No stars means no stellar nucleosynthesis, the process by which stars forge heavy elements from lighter ones. No carbon, no oxygen, no iron. The universe would be a cold, dark expanse of hydrogen and helium, slowly drifting, never igniting, never evolving. There would be no chemistry, no planets, no life. But let us set aside extreme reductions and think more carefully about what lowering the speed of light does to the geometry of spacetime itself. In Einstein's general theory of relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime caused by mass and energy. A massive object, a star, a planet, a black hole, bends the fabric of spacetime around it, and other objects follow the curved paths that result. What we call gravitational attraction is really objects following the straightest possible paths through a curved geometry. The speed of light enters this picture in a profound way. It determines how strongly spacetime curves in response to a given amount of mass. Lower the speed of light, and the curvature of spacetime around any given mass increases dramatically. Objects that are not currently black holes would become black holes. The Earth, the Sun, perhaps entire galaxies, their spacetime curvature would intensify beyond the point of no return. A universe with a much lower speed of light would be a universe dominated by black holes, regions from which nothing, not even light, could escape. Matter would collapse inward almost everywhere. The open, expansive universe we inhabit, with its galaxies and voids and long stretches of navigable space, would not exist. There is another dimension to this question, literally. One of the consequences of special relativity is that as an object moves faster, approaching the speed of light, time for that object slows down relative to a stationary observer. This phenomenon, called time dilation, has been confirmed experimentally many times, including in measurements of unstable particles accelerated to near light speeds, and in the precise timing of atomic clocks aboard aircraft. The speed of light sets the scale for this effect. When the speed of light is very high, as in our universe, you have to travel extraordinarily fast, a very significant fraction of 300,000 kilometers per second, before time dilation becomes noticeable. At human scales of motion, the effect is real, but utterly negligible. Now lower the speed of light to, say, the speed of a running person. Suddenly, time dilation would be an everyday experience. Walking from one side of the room to the other would measurably age you more slowly than someone standing still. A person who spent their life moving at a brisk pace might age perceptibly more slowly than a sedentary one, not metaphorically, but physically, biologically, in actual elapsed seconds. The geometry of spacetime would be woven into the texture of ordinary experience. Time would be visibly, tangibly personal, not shared, not universal, deeply individual, in a way that would make human civilization as we know it almost unimaginable. How would you coordinate a meeting if time itself ran at different rates, depending on how fast each participant was moving? How would contracts, history, memory, or shared experience function in a world where time was not even approximately the same for everyone? Consider one more consequence. In our universe, we can see galaxies billions of light years away, objects so distant that the light we receive from them left before the Earth existed. The observable universe is a vast sphere, its radius determined by how far light could travel in the age of the universe. Lower the speed of light, and that sphere shrinks. Not just because light travels less distance in a given time, but because the universe itself, its expansion, its thermal history, its causal structure would be entirely different. In a universe where light moved very slowly, the observable universe might encompass only a tiny neighborhood of space. Everything beyond that neighborhood would be, in the most literal sense, unknowable, beyond the reach of any signal, any influence, any connection whatsoever. Observers in such a universe, if they could exist, which, as we have seen, is doubtful, would be profoundly, cosmically isolated, not just separated from other civilizations by distance, but separated from most of reality itself, with no possibility of ever knowing what lay beyond their small bubble of causally connected space. Now we arrive at something that surprises even those with some familiarity with physics. Many people assume that the speed of light being the universal speed limit means nothing can go faster than it, and that this is simply an engineering constraint, like a posted speed limit on a highway. Given a better engine, perhaps we could exceed it. This misunderstands what the speed of light is. The speed of light is not a limit imposed on top of the universe. It is embedded in the structure of the universe. It is the rate at which causality propagates, the speed at which cause can produce effect across space. To exceed it would be to go very fast. It would be to go backward in time from the perspective of some observers. This is not a speculation. It follows directly from the mathematics of special relativity. If information could travel faster than light, then in certain reference frames, certain states of motion, that information would arrive before it was sent. Cause would follow effect. The logical structure of events would invert. This is what physicists mean when they say faster than light travel would violate causality. Not that it would be technically difficult, but that it would require the universe to allow effects to precede their causes. The universe, as best we can determine, does not permit this. But here's the deeper and perhaps more astonishing truth. The speed of light did not have to be the same for all observers. That is not obvious. That is not a logical necessity. It is a feature of the universe we inhabit. A feature that happens to make causality coherent, that happens to make the laws of physics the same everywhere, that happens to allow the existence of stars, chemistry, and life. The constancy of the speed of light is not merely a measurement we made. It is a hint, perhaps the deepest hint we have, about the underlying symmetry of spacetime, about the fact that the universe is, at its root, profoundly democratic. The laws of physics do not favor any observer, any frame of reference, any position in the cosmos. That democratic principle, that no vantage point is privileged, is perhaps the most powerful and far-reaching idea in all of modern physics, and the speed of light is its clearest expression. There is one more counterintuitive point worth dwelling on. When we ask, what if the speed of light were slower, we are implicitly assuming that everything else would remain the same. The size of atoms, the strength of gravity, the age of the universe, and only this one number would change. But this is not how physics works. The speed of light does not stand alone. It is entangled with other constants of nature, the charge of the electron, the strength of the electromagnetic force, the mass of the proton. These constants are not independent knobs you can turn separately. Change one and the others may shift as well, because they are related by deep mathematical structures we are still working to understand. When physicists study the question of what would happen if fundamental constants had different values, they are really asking a question about the space of possible universes, the landscape of physical law. And what they find, consistently, is that the universe we inhabit sits in a remarkably narrow region of that landscape where stars can form, chemistry can operate, and complexity can arise. Whether this is chance, or necessity, or something entirely else, remains one of the profound open questions of physics and cosmology. We have followed light through thought experiments, through the geometry of space-time, through the structure of stars and the fabric of causality. Now, let us pull back. Let us think about what we are in light of what we have discovered. You are made of atoms. Those atoms were forged in the cores of stars, stars that lived and died billions of years before the sun was born. The carbon in your body, the oxygen in your breath, the iron in your blood, these were all synthesized in stellar interiors and scattered across space in stellar depths, and they came together in this solar system, on this planet, and eventually in you. That process, that chain of events from hydrogen clouds to human consciousness, was possible only because the speed of light was large enough to allow stars to shine for billions of years. Only because the relationship between mass and energy was rich enough to sustain nuclear fusion across cosmic timescales. Only because space-time was curved gently enough to allow open, expansive structures like galaxies and solar systems to exist without collapsing into black holes. You are a consequence of a very specific value of a very specific number. This is not mysticism, this is physics. And physics, at its best, does not diminish wonder, it deepens it. Consider time. In our universe, the speed of light being as large as it is means that time dilation is imperceptible at human scales. We all share, approximately, the same time. History is something we can discuss coherently. Memory is something we can compare. Civilization, the accumulated knowledge of generations, the slow construction of science and art and understanding, is possible because time runs at nearly the same rate for all of us. In a universe with a much slower speed of light, that shared time would dissolve. History would be a personal experience, not a collective one. The concept of a civilization, a society that persists and accumulates and builds, might not be coherent at all. We take shared time for granted. We should not. It is a gift of physics. Consider space. The speed of light determines the size of our observable universe, the region of space with which we can, even in principle, have any causal connection. In our universe, that region is immense. Hundreds of billions of galaxies, an incomprehensible wealth of structure and complexity. We have only visited one world beyond our own. We have sent robotic probes to a handful of planets and moons. We have pointed our telescopes at galaxies so distant that the light we see left before life arose on Earth. And yet, all of this is accessible to us, at least in principle. The universe is not hiding from us, it is broadcasting. What would it mean to live in a universe so small that no signal from beyond your own star system could ever reach you? Where the night sky was simply dark, with nothing to see, no message to receive, no hint that anything else existed. Such observers, if they could exist, would have no astronomy, no cosmology, no knowledge of the universe beyond their immediate surroundings. They would not know they were in a universe at all. We, by contrast, can see 13 billion light-years in every direction. We can read the story of the universe in the light that reaches us. We can trace the evolution of galaxies, the birth of stars, the large-scale structure of space itself. The speed of light being as large as it is means we are cosmically connected, not just to our neighborhood, but to a vast, ancient, extraordinarily rich expanse of reality. That is not something to take lightly. And finally, consider knowledge itself. Physics in the last century has revealed that the universe operates by laws. Not arbitrary laws, but deep structural principles, symmetries, conservation laws, geometric relationships that appear to hold everywhere, at all times, for all observers. The constancy of the speed of light is one of those principles. and the history of discovering it, understanding it, tracing its consequences through special relativity, general relativity, quantum field theory, and beyond, that history is one of the great intellectual achievements of our species. We are a universe that became aware of itself. We are matter that developed the capacity to ask questions about the laws that govern matter. We are, in the most literal sense, the cosmos reflecting on its own structure. The speed of light is 299,792,458 meters per second. That number is not arbitrary. It is not a human convention. It is not a measurement error. It has been confirmed by countless experiments in laboratories and observatories across the world, across decades, across the full breadth of humanity's scientific effort. And it is just right. Not in a sentimental sense, not in a designed sense. Physics does not tell us whether it was designed, but right in this sense. Given that number, the universe can have stars. It can have chemistry. It can have time shared among observers and space explored by signals and history accumulated across generations. Given any significantly different value, the universe becomes dark or collapsed or causally isolated or too brief to matter. We did not choose this number. We discovered it. And in discovering it, we discovered something about ourselves, that we are the kind of creatures the universe produces when the number is right. That we are, in the most literal sense, the children of the speed of light. When you look up at the night sky, you are receiving a message. Photons that traveled across space for years or centuries or billions of years, arriving at your eyes, carrying information about their source. The universe is speaking to you at the only speed it knows how to speak. It is worth listening.